Now we'll discuss about the pipeline performance. Till now we have discussed that how pipeline improves the performance by executing more than one instruction and giving them inside in the processor, and in different states will be busy in doing different instructions, executing different instructions over there. But however, there are variety of reasons for which the pipeline may not be able to complete its task. So for a variety of reasons, one of the pipeline stages may not be able to complete its processing task for a given instruction in the time allotted. For example, in our previous example that I have taken, assuming that every stage takes one clock cycle. So instruction 1 will fetch in one clock cycle 1, decode in clock cycle 2, execute in clock cycle 3, memory operation in clock cycle 4, and write back operation in clock cycle 5. However, this may not become true for the instruction 2. Instruction 2 may go for fetch in the second clock cycle as the first instruction in the decode, second instruction will fetch in the second clock cycle. When the instruction 1 goes to execute, 2 will go to decode, instruction 3 can be fetched. Now, when the instruction 1 is in the memory, instruction 2 may be given for execution. The instruction 2 is supposed to finish the execution in clock cycle 4. But due to some reason, maybe hardware or some operand or something is not, instruction is not found, for which instead of one clock cycle, it takes 3 clock cycles for execution. Now, instruction 2 will finish execution in the 6th clock cycle and start the memory operation in the 7th clock cycle. As the instruction 2 has not released the execution stage, therefore instruction 3, although it has decoded its task, it cannot be sent to the execution because execution is already occupied by the instruction 2. When the instruction 2 goes to memory, then only the instruction 3 can go for the execution stage. Now you can see over here, instruction 2, which is supposed to be completed in clock cycle 6, now it is completing in clock cycle 8. So we have a penalty of 2 clock cycle over here. This 2 clock cycle penalty is not only for instruction 2. Instruction 3, which is supposed to be completed in 7, now it is completing in 9. Instruction 4, which is supposed to be completed in 8, now is completing in 10. So this 2 clock cycle penalty is for all subsequent instructions to be executed. So this penalty, these ideal periods, each ideal periods are called the stalls or bubbles. So we have 2 bubbles, 2 clock cycle penalty over here in the pipeline. And why these bubbles occur? Because of some reason. So any condition that causes the pipeline to stall is called a hazard. So what is hazard? Hazard is the condition for which the pipeline stalls. Why these stalls occur? Because of some reason. Those reasons are called the hazards. And there are 3 types of hazards that may occur in a pipeline. The first is called the structural hazard. The situation when 2 instructions require the use of a given hardware resource at the same time. That means more than one instruction requiring the same hardware. For example, is a common bus. To common bus, multiple instructions wants to transfer the data. Then, as you know that if it is a common bus, only one transfer can occur at the same time. So therefore, other instruction has to wait. If you have one ALU but multiple instruction fetch, even if you fetch multiple instruction, if you have one ALU, it can execute only one task at a time. So other instruction has to wait. So as it has to wait, therefore structural hazard occurs. Why hazard occurs? Because ALU was not enough ALU was available. Hardware is not available. There might be a chance the register file has not enough ports for read and write. There is a register file which contains all the registers. However, it has a limited number of read and write ports. If you have 2 read ports, then only 2 instructions can be read at the same time. If you have 1 write port, one instruction can be written at the same time. So if multiple instructions wants to write, then other instructions has to wait. So this occurs because of what? Because of the non-availability of the hardware. The second kind of hazard is called the data hazard. It is any condition in which either the source or the destination operand of an instruction are not available at the time it is expected in the pipeline. So in structural hazard, at the time we expect the hardware, that hardware is not available. In data hazard, the time it is expected in the pipeline, the data is required, the data is not available. If the data is not available at the time it is expected in the pipeline, then we say the data hazard or operand hazard. Suppose in an instruction R1 equals to R2 plus R3 and R2 is not available. It cannot do the operation, it has to wait. We say it wait because of data is not available and it is data hazard. The next one is the control hazard. The pipeline may also be stalled because of a delay in the availability of the instruction. Instruction may not be available. If there is a catch miss, it wants to read the instruction 5 after 6 and 6 is not available, it's a catch miss, then the pipeline has to wait. It arises from the pipelining of branches and other instructions that changes the PC. There might be a chance that we expect the instruction 6 to be executed after instruction 5, but if there is a branch instruction, so the instruction may jump into some other instruction, maybe instruction 10, and instruction 10 may not be available. So in that case, we say control hazard has occurred. Now, what is the performance of pipeline with stalls? If the stall is there, how the performance is being affected? The speed up, we know that average instruction time in a on pipeline by average instruction time in a pipeline architecture, the time it takes by not using pipeline, the time it takes using pipeline. So how much time it will take in on pipeline architecture is the CPI of on pipeline into clock cycle, number of clock cycle required into clock cycle time. Similarly, for pipeline architecture, number of clock cycle required into clock cycle time. The clock cycle time are same because the same machine is being converted to a pipeline. So clock cycle time is same, but the number of clock cycle required may vary. So CPI on pipeline by CPI pipeline into clock cycle on pipeline by clock cycle pipeline. Now, if these two are same, so this can be cancelled. So we are left with CPI on pipeline by CPI pipeline. Now, what is this CPI pipeline? How much clock cycle it will take in a pipeline architecture? It says that ideal CPI plus if any stall occurs, the pipeline stall clock cycle per instruction. If the ideal CPI will assume as 1, then 1 plus pipeline stall clock cycles per instruction. So there might be some stalls. If this is 0, then this is your ideal CPI. 1 plus 0 is 1. So that means CPI of the pipeline become 1. But there might be some stalls may occur in the pipeline. So now it becomes speed up equals to speed up on pipeline by 1 plus pipeline stall clock cycles per instruction by substituting this one. CPI on pipeline is nothing but the pipeline depth. The depth of the pipeline plus 1 plus pipeline stall. So from this we can say speed up equals to pipeline depth by 1 plus pipeline stall clock cycles per instruction. Why you say it's a pipeline depth? CPI on pipeline is nothing but the processor is divided into number of stages, and that number of stages entirely is the on pipeline one. From this we can conclude that speed up is directly proportional to the pipeline depth or the number of stages and inversely proportional to the pipeline stall clock cycles per instruction. More the number of stages, better is the speed up. However, more the stalls, the speed up is less. Now, how to overcome this structural hazard? So we know that there are 3 types of hazards: structural, data, and control hazards. Now, how to overcome the structural hazard? Unfortunately, the structural hazard cannot be overcome by any other straightforward method, any alternative method. The only solution is to introduce multiple resources. If the hardware is not available, you make the hardware available only. So if suppose you have keeping data and instruction cache in different location. If you have common cache, you keep data and instruction in different cache. If you have register file has limited number of ports, you introduce multiple ports. If you have a single bus, you go for multi-bus architecture. If you have one ALU with multiple instructions page, you can go for additional ALUs. So there is no alternative solution for the same. So therefore, we do not have more emphasis on this structural hazard. Only solution is there to introduce multiple number of resources. Now we'll go for the data hazard. Data hazard is a situation in which pipeline is stalled because the data to be operated on are delayed in some region. That means what is not available, the data is not available. We'll take an example over here. Suppose instruction 1 is A equals to 5 into C, instruction B is 20 into A. The instruction 2 can only start its execution when the instruction 1 completes. Unless the instruction was not written the result into A, the instruction 2 cannot read it. So we must ensure that results obtained when instructions are executed in a pipeline processor are identical to those obtained when the same instructions are executed sequentially. So if you go for executing instruction 2 by taking the previous value, then this B will get a wrong result, incorrect result. So the instruction 2 has to wait till the instruction 1 is completed. So look over here. If you look into this time space diagram, instruction 1 fetch, decode, execute, memory, and write back. So instruction 1 will write into this A in the 5th clock cycle. In the meantime, instruction 2 has fetched because instruction 1 is in decode, second one is fetched. It has gone for decode, but out of these two operands, only 20 is available, value of A is not available. So only we are writing to A, only half of it have done, but another half it has to wait till the instruction 1 will write in the 5th clock cycle, so that instruction it can read in the 6th clock cycle. So decode will over in the 6th clock cycle only, and then it will go for execution and write back. So these clock cycles are being wasted. So although the instruction 3 is fetched in the clock cycle 3, it can do decode in the clock cycle 7 because instruction 2 is in execution, then the 3 can go for decode, and subsequent the other instructions are. Now look over here, instruction 2, which is supposed to be completed in 6, now in completing in the 8th clock cycle. This is memory and write back, wrongly written. This is memory and this is write back. So which is supposed to be completed in the 6th clock cycle, it is completing in the 9th clock cycle. So we have a penalty of 3 clock cycles over. And this 3 clock cycle penalty is for all the instructions. And why this 3 clock cycle penalty occur? This 3 clock cycle penalty occur because the operand was not present. The A was not present over here. So how to overcome this data hazard? One of the solution is the register write occurs in the first half of the clock cycle and register read occurs in the second half of the clock cycle. So it says that in a clock cycle, generally we do one operation, either read or write. It says in one clock cycle, half of the clock cycle, first half of the clock cycle is used for writing and second half of the clock cycle will be used for reading. So in a clock cycle, first half will be used for writing and second half will be used for reading. That means if it is in 5th clock cycle, while it is writing, in the same clock cycle also it can start reading. In the previous case, what you have, when it is writes, the next clock cycle it reads. If you have such circuits so that writing and reading can be done in the same clock cycle, then it will complete in the 8th clock cycle. We have 2 clock cycles stop. That means at least we have reduced 1 clock cycle penalty. Another method is the data forwarding or operand forwarding or result forwarding. This is an effective method for reducing the data hazard. See over here in our previous example, the first instruction is writing to A, the second one is reading from A. The second instruction is really dependent on this value of A or the value of 5 into C. If you get the value of 5 into C, the instruction 2 can continue its execution because it is writing to A in the 5th clock cycle. However, type into C operation, ALU operation can be done in the third clock cycle. So looking into this, this is the ALU which take two inputs over here. It is does the operation and the result. Result is the first instruction is what? The first instruction is suppose add R1, R2, R3, multiply R7, R1, R5. Now these two instructions are being added and it will be stored in R1. Second instruction is reading from R1, therefore there is a dependency. Now when R2 and R3 is given over here, it doesn't produce R1. R2 plus R3 doesn't produce R1, rather R2 plus R3 is produced over here. Writing to R1 will be done in the write back stage. The result which is obtained after the ALU can be forwarded to one end of the ALU. So this R2 plus R3 can be given over here to the ALU, and this R5 can be given over here so that the next instruction can continue. So data are available at the output of the ALU once the execution stage completes. Data is available over here. However, writing operation is done in the write back stage. Hence, the delay can be reduced or possibly eliminated if we arrange for results of instruction 1 to be forwarded directly to use in the third execution step of 2. So first instruction, after the execution stage, the result is available, which can be forwarded to the execution stage of the 2. But the instruction 2 can continue its execution, and there will be no hazard. The 5th clock cycle instruction 1 completes, in the 6th clock cycle the instruction 2 completes. So there will be no stall. So data forwarding is an effective way of reducing the data forwarding. That is another way of handling the data hazard is in the software. So what we can do, we can have, suppose that we see there is a dependency between instruction 1 and 2. Instruction 1 is writing to R2 and instruction 2 is reading from R. So instruction 2 is dependent on instruction 1. Instead, by knowing that there is a dependency and 3 stalls will occur, we will insert 3 instructions over here. Those are called the NOP instructions, no operation instructions. These instructions will not do anything. It will only pass through the pipeline. Now, what is the advantages of this? What is the difference between this NOP and stall? The stall will make the pipeline to halt. The pipeline will not continue. Here, the pipeline will continue without doing any task. So, NOP is actually an instruction. As NOP is an instruction, it can be replaced with any other instruction. So we'll try to find some useful instruction and we'll replace over here with this NOP slots. We assume that data dependency is discovered by the hardware while the instruction is being decoded. The compiler can introduce some delay cycles needed between the dependent instructions by inserting NOP instructions. So it will insert some NOP instructions over here. So being aware of the need for a delay, the compiler can attempt to reorder instructions to perform useful tasks in NOP slots and thus achieve better performance. So these NOP slots may be filled by some useful instructions. So in the meantime, the dependency can be resolved. It will execute some other instructions over here which are not dependent on this instruction 1. But there are some drawbacks. As the code size increases, a given processor architecture has several hardware implementation offering different features. NOP instruction inserted to satisfy the requirement of one implementation may not be needed and hence lead to reduced performance on a different implementation. Suppose we have a processor which requires a 5-stage pipeline and require 3 NOP slots. The program is executed in some other architecture where it is only 1 NOP is required. As you have already given 3 NOP instructions, therefore, or two NOP instructions are being wasted. Or this can be executed in another processor which having 10 NOP slots are required, then it is of no use. We have read that the data forwarding is useful for reducing the data hazard. However, there are some situations where the data forwarding fails. Unfortunately, not all potential data hazards can be handled by bypassing. We'll take an example over here. The first one is a load operation, R1 0 of R2. So it loads into R1. There's a subtract instruction, R4 equals to R1 minus R5. Now see over here, the first one is a load operation. And we know that load operation is done in memory stage. So instruction 1, fetch, decode, execute, memory, write back in the 5th stage over here. So data is available to R1 only in the memory stage, not in the execution stage, because it is a load operation. I've already told you load and store is done in the memory stage. So in the memory stage, the R1 will get its value. But at that time only instruction 2 is in the execution stage. Data can only be forwarded from when it is available. That means if it is available in the clock cycle 4, it can be forwarded to clock cycle 5. But if the data is there in the 4th clock cycle, it cannot be forwarded to the 4th clock cycle itself. So therefore, data cannot be forwarded into this execution stage. So forwarding path cannot operate backward in time. Forwarding path cannot operate backward in time. So here it is failed, and here a stall will definitely occur. So all potential data hazards cannot be handled by bypassing. So data hazard may occur. We cannot give a guarantee that all data hazards can be removed. So the next class will go for the branch hazard.